Today I'm going to show you through the Q-learning update algorithm and what happens when you vary each of the hyperparameters one at a time, just at a very high level. So this is based on the GYM library, which is produced by OpenAI as a sort of standardizable, like standard or standardizable framework for reinforcement learning for industry and research. These are the performance metrics we'll be looking at, which are the total reward, which is sort of an overall estimate of the competence of the learner, the step counts, which is an estimate of its efficiency. Lower step counts on average are better, and the penalty counts, which is an estimate of its precision. Fewer penalties are better. So this here is basically the heart of the Q-learning update algorithm. At every step in what is a goal-oriented process, the learner first kind of takes a dice roll, which determines whether or not it tries something new at random, or whether it chooses the highest known expected value action from the actions that it has available. So it's like, all right, here I am. What am I going to do? The thing that I know works well, or something new. Generally, a higher epsilon encourages more exploration and covering more ground and learning more about the world that the learner inhabits. It's good early in the training process, but a lower epsilon is more conservative and tends to result in fewer penalties lower on once the world map is pretty well built. So then the environment provides some kind of reinforcement, and from that reinforcement, the learner updates the value in its Q table, in its state action pair table. And that action has a value that is based largely on the old value. There's an exponentially weighted average. The base of the exponential is determined by alpha. So if alpha is 0.01, then 1% of the value in the Q table is updated to reflect the value learned from the newest experience, while 99% remains whatever it believed before that last thing happened. And then it's also based on the best possible position that action puts the learner in. So next max represents the best next move that's available once a move is completed. And then gamma is the future discount rate, which determines how much of that future value is included in the value of the new action. So a low gamma means there's a relatively low value placed on the future, while a high gamma means that there's a relatively high value placed on the future. Tomorrow is worth nearly as much as today. Whereas low gamma is like YOLO, right? And then the Q table is updated, and here we're keeping track of these performance metrics. And it keeps learning. It tries the next thing until it completes a task, and then it completes more tasks until it knows what it's doing, and then it knows what it's doing when it's completing tasks. It's a robot. That's what its life is about. So we'll look at what happens when we assign some default values for alpha, gamma, and epsilon that are just like basically reasonable. They're not optimized for anything, but they're reasonable. But then we'll train several learners with different values of alpha, going from a range of values from like 1 part in 10,000, so it's a very low learning rate, to 0.4, which is a really high learning rate. Normally alpha is like no more than 0.1. We'll do the same thing where we hold alpha and gamma steady and look at different epsilons, and then hold the other two steady and just look at different gammas. So here's some code that just like chooses our plots, and so we'll be looking at the net reward for the entire duration of the learning period, as well as a zoomed in reward for just the first 5,000 steps, and just the first 5,000 ethics. And then we'll look at the same thing for the step count and the penalty count, and this is what we get. This is like one of those baking shows where they put a raw chicken in the oven and then immediately pull a cooked chicken out of the second oven. These learners were already trained up in advance. Each one takes about a minute, give or take, to get through. Sometimes longer, especially the ones with like really extreme values. So here's some that are already trained up and plotted out. So starting with this really low alpha, we can see that even after 100,000 epochs, the net rewards has not converged. And when we zoom in, we can see that this is how quickly it's not converging for the first 5,000 epochs. And similarly, we can see the step count is still not converged. It hasn't found a simplest or most efficient set of routes through this world. And this is a perfectly stable environment. A perfectly stable environment that's fairly simple, where there's a finite number of possible tasks. They're always the same. And there's no variation in the payoff. So this is like the simplest possible scenario. And similarly, the penalty count is still like definitely not yet leveled off, even after 100,000 epochs, with this very, very low alpha. We move alpha up a little bit, and all of a sudden, this is like way more level, even just like after, certainly by the 50,000 epoch mark. By 5,000, it's leveled off a lot more than the one with the lower alpha. And so as we go through these different alpha values, these are ascending, we can see that at some point, it just like memorizes stuff after its first few times through. So this is alpha is 1 part in 20, 0.05, 5%. And alpha at 10%, 20%, 30, and 40. You might infer from this that you might as well just use the highest learning rate, memorize the world as fast as possible, and, win promptly. But remember that this is only true in an extremely stable, steady world where nothing ever changes and all of the results are the same no matter what you do. So a high alpha does result in memorization, but in a world where anything changes, a high degree of memorization isn't necessarily the best way to go. So when we look at different gammas, so this is a different future discount rate, we'll see that with a very, very low gamma, here we're rating the future as being worth only 10% as much as the present. That's to say the immediate future, the very next step. We have some kind of odd behavior where things kind of level off, but then they get weirder sometime after 50,000 epochs. And that's true for all three of the performance metrics that we're looking at here. It's not evident on the zoomed in ones, but you can tell that something odd starts happening around maybe the 70,000 epoch mark. It gets listless. That's not so much the case for gamma is about 50%, or 60%, or 70%. These higher weights on the future, higher valuations of the future, lead to more stable behavior, whereas the ones with the low rates on the future, they get a bit peculiar. And then lastly, when we look at epsilon, and we look at these different values of epsilon, we'll start with a very small epsilon, which is to say that it only tries something new at random 1 in 200 times. And basically it tries everything that's possible in the first few times, like the first few epochs. I can't even tell, like even zoomed in, it's hard to tell how long that's taking. Maybe 100, and then everything stays the same for the rest of time. It tried everything because it tried every possible combination, because it was, I don't know, very slow to try new things. That may not be the best interpretation, eh? Basically, it finds a set of things that works and sticks to it because it is very, very not exploratory. Here we have a more exploratory learner, and we can kind of contrast the difference when we look in the zoomed in version at 5,000 epochs. It takes a little bit longer to converge, but not much longer. The epsilons with sort of more middling values closer to 0.1 might be the most efficient. And then we end up with really peculiar behavior for the learners at the higher epsilon, where they figure things out really quickly, and then it's like they just mess around too much, trying random stuff because they can. And if they ever converge on a world map, they don't actually use what they know. So a high epsilon here, it's just trying random things 30% of the time, is certainly not helpful, but a super minimal epsilon is also not optimal. Now, remember that this is for a perfectly stable, perfectly predictable, perfectly reliable environment. These never occur. Like, in any application where you actually need to use machine learning, you won't find these conditions. So on the next video, we will look at the effects of varying one hyperparameter at a time in an environment where there is chaos and where learning is a little bit more challenging. And you'll start to see some of the nonlinear effects of varying each hyperparameter. Thanks so much for watching, and we'll see you next time.